mathematical physics class. I'm Dr. Sunil Kedia as your guide here. I'll be teaching you mathematical physics, and this is my third class. You can see the videos of my previous classes where I have introduced the background of why we have started this lesson, and in the second class and a bit in the first class we have introduced some of the initial discussions on mathematical physics. We have started with the vector analysis, scalars and vectors, and as I had told you in my previous classes, I am referring to one of the books in mathematical physics. You can see the book here. It's Mathematical Methods for Physicists, a concise introduction by Taicho, and we have discussed that in our subsequent classes we will be changing different books and referring to different guides, so that we will have complete idea of what are the things that one engineer or scientist should learn in mathematical physics. Since we have just 2 classes in the course tutorial so far, we are into the basics, and I'll strongly suggest everyone of you to go back to the previous videos and just watch them. There is not much technical in them because they are just the beginning of the tutorial, but it will certainly help you, bring you to the same page where we are now. And in this class we'll discuss something about the vector algebra. So like we had already discussed, scalar quantities are those quantities that we deal with every day, and because we deal with them every day, we know how to add them, subtract them, or even multiply them or divide them. Like 5 kg and 10 kg can be added or multiplied or divided in any way you want, or 5 meters and 10 meters can be used for any mathematical operations in our day-to-day life. But if a quantity comes with a direction on it, say 5 degree north or 5 meter north and 3 meter south, then we don't know the resultant vector. Means if somebody moves from a point towards north for 5 meter and then he changes his direction towards south for 3 meter, then where will he be? Yeah, of course he will be at the point that connects the origin and the final destination. But how to mathematically represent that? Because these two are vector quantities, and in order to understand the final point the person has arrived, we need to understand how the vectors are added or subtracted or divided or multiplied, because those things will only guide us on how to add 5 meter towards north direction and 3 meter towards south direction. So without adding these two parameters we will not probably reach to the point where we want. So I believe that let's go to the discussion here and learn the basics of the algebra, and then probably we'll do a lot of problems to to make ourselves comfortable with vector algebra, and we'll do some real world calculations, and we'll discuss some of the quantities that are vectors, and why those are vectors and why some other quantities are not vectors, and what are the importance of a vector quantity. Why do we need to know a vector quantity? Because these things will be, in the subsequent classes, these things will be useful, and that is why it is necessary to learn the basics of scalars and vectors now. I'll quickly go through what we had learned in our last class, so that it will be easier for you to grasp some points. We have seen how a vector can be represented in a three-dimensional space. We are told that this is x, top is y, and this one is z. So z is the vector that is coming out of the page, and we have represented this vector as it has some components towards x, y, and z direction, and all three components are represented as this towards x, a1 towards x, a2 towards y, and a3 towards z, with I cap, j cap, and k cap, which represents the directional unit vector towards x, y, and z direction. And then we had discussed something called direction cosines. These direction cosines are basically cos alpha, cos beta, and cos gamma. Those direction cosines are very handy to find out the value of unit vector towards a certain vector. So if you know the alpha, beta, or gamma of a vector, let us say this is a vector, and you know the alpha, beta, and gamma, the angle that they create with x, y, and z axis, then you can probably find out a unit vector whose magnitude is just 1, but the direction is same as this vector. So if you multiply this unit vector with any other vector, that will the outcome of that product will be a vector which is parallel to this original vector. So direction cosines are very handy stuffs, and we'll see how these direction cosines are used in some of the problems. But for now we need to understand some of the other characteristics of a vector quantity. So we'll move to the vector algebra. But before that, as we had discussed in a previous class, that a vector A, which is bold-faced in this book, can be represented as, in a parenthesis, A1, A2, and A3. This A1, A2, and A3 are the magnitude of the values towards x-axis, y-axis, and z-axis. So if I have a vector A that is represented as this A1, A2, A3, so I'll just start here. I'll write a vector algebra, and we were discussing if a vector is written as A1, A2, A3 like this, so we can also write this vector as A1 plus A2 plus A3, and then this one is I cap, this one is j cap, and this one is k cap. So remember I had discussed this, the I cap is the unit vector towards x-axis, j cap is the unit vector towards y-axis, and k cap is the unit vector towards z-axis. So you know, if you have to draw this vector, this is a vector quantity, and if I have a three-dimensional space like this one, and if here it is x, this is y, and the out of plane, in and out of plane is z, here z or g, whatever we call it, then we'll have to first move towards x-axis. The distance will be a1. It can be anything in numerical form, and then we'll move towards y-axis, which is a2, 2, and then we'll come out of the page towards z-axis, and the distance will be a3, and when we finally reach here, we'll join the origin of this vector. We'll join like this, and this will be our a vector. So finally we arrived at the vector with its resolved components. These are called the resolved components because they are resolved towards a unit direction, and since these are universal, I cap and j cap and k cap, it's very easy and handy stuff to learn and understand. So now we'll go up to learn some of the vector algebra. So I'll just go down the page so that it will be easier for us to see. Here we come. So there are some of the basic assumptions that we need to understand first. If two vectors are equal, like there is a vector A and there is a vector B, if they are equal, that means their unit vector, the magnitude of their components towards x, y and z directions are also equal. Means essentially A1 has to be equal with B1, A2 has to be equal with B2, and A3 has to be equal with B3. If any of these three component doesn't match, then these two vectors will not be equal. It's agreed, right? In coordinate geometry, if you are moving towards x, y and z by different lengths, you will end up at a different point, so the vectors will not be same. And if these three are equal, then A vector has the same direction compared to B vector, and the length of these two vectors are same, exactly same. If for instance okay, we'll come to that at a later point. So this way it has to be represented. Now we'll go to the vector addition. So if I have a vector A and a vector B, vector A can be represented as A1, A2 and A3 in parentheses. B is represented as B1, B2, B3 in parentheses. So how do we add them? As simple as this. You have to add component wise, means whatever component is there for A1, A towards x-axis, that has to be added with the component of B towards x-axis. So you have to add the first component with the first component of B, that is A1 plus B1, comma A2 plus B2 and A3 plus B3. So the resultant vector will be A1 plus B1 I cap, A2 plus B2 j cap and A3 plus B3 k cap. So you'll have a different vector here, but it will be the summation of A vector and B vector. Okay, so the sum of two vector is again a vector that has to be stretched out here, because you'll come to a place where you will find that some of the operators make the outcome scalar. There are no more vector. So here we need to understand that sum is always a vector quantity. Sum of two vector quantity is a vector quantity. That let me write it out here. Sum of two vector quantities is a vector. Sum of two scalar quantities is a scalar, means without direction. So we have seen how it's quite easy, right? Sum of a vector is a vector. Sum of two vectors is vector and sum of two scalars is scalar. So it's quite obvious. Now we'll go to second paragraph. What it says: we can add two non-parallel vectors by graphical method, but I'm not going into graphical method now. I have a small application that we'll discuss in our subsequent classes. That will make us understand how the graphical method can be used easily. For now, we are skipping that. To add a vector B to vector A. So we are skipping this part. What if this is a vector addition? What if we want to subtract two vectors? So let us say I have a vector A and I want to subtract it vector A, and I want to subtract another vector B from here. So how we will write? I'll say it will again start with a parenthesis, the first vector's component minus B vector's x component, comma A2 minus B2, comma A3 minus B3. So it's quite obvious, like addition subtraction also follows the same rule, and let me stress it. I'll write another stuff here probably. Subtraction of two vectors so it's quite obvious, right? Like addition subtraction is also a vector quantity. So you know whether you're adding or subtracting two vector quantity, you will get a vector quantity. So now let's see what happens when a scalar quantity is multiplied with a vector quantity. C is a scalar quantity, you see it's italic, and A is bold faced, so you know A is the vector quantity. And what happens if C is multiplied with A? A scalar is a multiplied with A. So A vector can be written as A1, A2 and A3, and this scalar quantity multiplies with each component. So it goes with A, with A2 and with A3. So obviously the product is also a vector. So if you see geometrically, let us see it in the graph. So I have a axis x, y and z. I had a vector like this, and now I am trying to make another vector, which is, this vector is, let us say, A, and now I am trying to make another vector which is 2 times of A. 2 is a scalar quantity, so it will be multiplied with its A vectors x, y and z component. I hope you can see it here. So let us see how it goes. So from here I'll start, and I'll go twice as the distance in x direction, twice in y direction. I'm sorry, y has to be down. Twice in x, twice in y, and twice in z. let me find it out. Twice here, and twice here. Okay, so the resultant vector will be either this on top of it, or it will be like parallel to it, and it will be like twice of the original vector. So if I have a vector quantity and if I am multiplying it with a scalar quantity, I'll get another vector quantity which is parallel to its original quantity. Like see here, if you have another vector called CA which is parallel to A, it will be C times longer than A. If C is -1, then the direction will reverse, because A will be then -A, so you will go towards negative x-axis instead of positive x-axis, and so on. So if C is a negative quantity, you will get the reverse of A vector. In that case, if A vector is going in this direction, you will get another vector which will go in this direction. It's just the reverse. It is -1A, and this one is A. So you will get a vector which is 180 degree apart, or they called anti-parallel. So we'll discuss how this vector addition works at a later time. So now we are coming to the subtraction. You see, subtraction a minus b can also be written as a plus minus of b. So from here minus of b means b in a reverse direction. And now if you have a vector, this is A, and if you have a b vector here, this is b, and if you want to do A minus b, you will probably draw b like this, and you will name it as minus b. Now you will take a vector this and vector this and add it up. We have not discussed how these vectors are added geometrically, but how it can be added mathematically, because we have seen here in just the previous page, if you add the x component of one vector with the x component of the other vector and so on, you will get a resultant vector that is the addition of two vectors. So instead of b, you will take minus b here and you will do the sum addition likewise. So finally you will arrive at a point where it is written as a1 minus b1, a2 minus b2, a3 minus b3, which is what we had discussed a few minutes back. So we saw the vector addition here, vector subtraction here, vector multiplication with a scalar quantity which is again a vector, and some of the vector addition properties, like vector addition is always commutative. A plus b will equal to b plus a. Even scalar addition is commutative. It follows associative properties like a plus b plus c equal to a plus b plus c. A plus 0 equal to 0 plus a equal to a plus minus a is 0. So you'll get a null there. So these are very common properties, and vector algebra follows these quantities, these properties. So now turn to vector multiplication. We have to understand how vector multiplication works. Note that there is no vector division. You cannot divide a vector, divide two vectors. So if you write like this, a vector divided by other vector, that doesn't mean anything in physics. So this is something that is like you'll never hear such things. But yes, if you divide a scalar, a vector divide a scalar by a vector, then it doesn't work either, because you cannot divide anything by a vector. Vector has to be on top always. So you can divide a vector by a scalar, but reverse is not known in physics terms. So this is by far very good, where you are learning how a vector is added or subtracted, and you also learn that there is no division. So out of the 4 tasks, you have learned 3: addition, subtraction and division, because there is no division, so there is no need to learn that, right? So now the last part is vector multiplication, and that is by far the toughest part. And since there is no division, we have divided multiplication into 2 categories: the scalar product and the vector product, or the dot product and cross product. So there are 2 kinds of multiplication that a vector can take place, a vector can operate with. So if there is no division, who cares? There are 2 multiplication ways. So we'll learn about the scalar and vector products in our next class. We're already 27 minutes in this class, so I think we can stop here. And in this class we have learned how vector addition and subtraction works, and I'm trying to go very slowly so that everyone will be getting what we are learning here. And I would encourage each of you to write some comments, some questions or suggestion in the comment box, and I'll be going through each of them, and I'll be responding to each one of you with the best answer I can give to a particular point. So in the next class we'll discuss the scalar product and vector product and how they are different. And just to give you a hint, scalar product gives the output which is scalar, and vector products gives the output which is vector. We'll discuss about it in a much longer detail, because these are a big thing to discuss in our next class. Till then, goodbye, see you, all the best.